We present SPAMs, structured-implicit parametric models. SPAMs are a deformable object representation that structurally decompose non-rigid object motion into part-based disentangled representations of shape and pose. Our approach enables a structured characterization of object movement, with part decomposition characterizing a lower dimensional space in which we can establish coarse motion correspondence. This allows us to effectively fit our part decompositions to new depth sequences with challenging motions. Our SPAMs are driven by a set of shape and pose latent spaces, whose structural partitioning into local regions is predicted by a part decoder. Each of the local spaces and the part decoder are characterized by deep implicit functions. The shape latent spaces learn to represent canonical space geometry by predicting SDF values. The pose latent spaces learn to deform the canonical space into a posed frame by predicting flow vectors. To fit to a new depth sequence, we establish part correspondences between the input observations on the left and our learned part spaces on the right. This guides a robust joint optimization between the shape and pose of all parts, which can even compensate for an arbitrary initialization of the pose. Here, for a single depth frame, we show how our test time model fitting converges across optimization steps, guided by our coarse semantic correspondences. In the following, we show qualitative results and baseline comparisons. We compare with IPNet and NPMs on the task of model fitting to depth sequences featuring very fast and complex motions. Note that we can retain high-frequency details, such as the jacket lapels. As shown in the sequence, we are also robust to loop closures. In comparison to the baselines, we can retain more hair and facial attributes. Additionally, we show that our structurally driven shape and pose representation enables robust fitting to sequences even without a learned pose initialization. For a given time frame in the sequence, we show here how the optimization evolves from a random pose initialization. Despite the very different initial pose, our part-based correspondences allow for our optimization to converge appropriately. In particular, NPMs requires a close pose initialization, whereas our approach maintains robustness to the pose code initialization. Thanks for watching.